The performance of the ripple carry adder is not always sufficient. In fact, it degrades rapidly with the increasing number of bits in the operands. This leads to the need for developing new adder architectures that provide lower propagation delays. To understand how latency can be reduced, let's analyze again carryout function, since it represents the critical path in ripple carry adders. This function can be reformulated by grouping the carry-in signal. So, Ci plus 1 becomes Xi and Yi, or Xi or Yi and Ci. Then we can rewrite the function as Ci plus 1 equals Gi or Pi and Ci, where Gi is Xi and Yi, and Pi is Xi or Yi. The functions g and p are called the generation and propagation functions. If gi is 1, a carryout is generated due to the values of the ith bits of the operands. If pi is 1, any incoming carry-in is propagated as carryout. It's important to note that gi and pi depend only on the values of the ith inputs, which means they can be computed in parallel for all n bits of the operands. By applying the refactored expression iteratively, that is, by reapplying it also to the carry-in Ci, we can observe that the value of Ci plus 1 can be made to depend only on Ci minus 1, as shown in the first equation reported in this slide. This substitution can be repeated until we reach carry signal C0, thus obtaining the formulation presented in the second equation shown here. We conclude that the carryout at any position can be computed using all generation and propagation functions up to that stage, along with the initial carry-in C0. Adders that use this technique of carry generation and propagation logic to compute carries in advance are called carry look-ahead adders. The structure of a 4-bit carry look-ahead adder is shown in the figure. In particular, we can observe that the carry-in of each stage, except for the first one, is generated by a dedicated module that takes as input the initial carry C0, along with all the generation and propagation signals from stage 0 to the current stage I. Then the bottom part of the architecture is composed of a set of full adders, each receiving the ith bits of the two inputs X and Y and carry in Ci, and computing the related result bit Si. It's important to note that there is no direct connection between these full adders, so they do not form a chain, as in the ripple carry adder. The bottom part of the slide presents the equations for the generation of the 4 carryout signals from C1 to C4. This confirms that this approach allows carryout values to be computed in parallel. Let's analyze the delays within the circuit. A delay of 1 logic gate is required to compute both the generation and propagation signals, either an AND or an OR gate. 2 logic gate delays are needed to compute the ith carry output, based on C0 and the corresponding generation and propagation signals from previous stages. An additional 2 gate delay is required to compute the ith sum output Si by means of the full adder. We report all these delays on the schematic in this slide. You can see that the maximum latency is therefore equal to the delay of 5 logic gates. Finally, it is worth noting that the latency of a carry look-ahead adder is independent of the number of bits in the operands and can therefore be considered constant. The discussed advantage of carry look-ahead adders comes at the cost of area. As the number of bits increases, the required logic blocks become larger and more complex. To address this issue, we move toward a modular architecture, such as the one used in block carry look-ahead adders. Just like with ripple carry block adders, we can also apply the block-based approach to carry look-ahead adders. A complete n-bit adder can be constructed by combining multiple m-bit carry look-ahead blocks. These blocks can be connected either in a ripple carry fashion or recursively using another carry look-ahead structure.